we're going to look at the concept in ANOVA of randomized block design. This is going to be a very similar concept to one we've already covered before for matched samples. So supposing I've got a population of people that do not go to the gym, and I've got the population of people that do go to the gym over here. So these people go to the gym. And I want to figure out if people that go to the gym weigh less than people that don't go to the gym. So I could take a sample of people that do not go to the gym, find the average weight, take another sample of people over here that do go to the gym, find the average weight, and I can do some sort of test and come up with a result. Two sample test and come up with a result. But the thing is that there may be problems with the result. People that go to the gym may end up weighing less than people that do not go to the gym, but that may not be a function of going to the gym. That may be a function of these guys having a healthier lifestyle. So maybe they have a healthier diet, and it may be the diet that is the reason for them weighing less, and it may not be going to the gym. So other issues can actually overwhelm the result. There could be gender issues, there could be age issues. People of different ages, different genders between the groups that you're comparing can lead to difficulties in your result, in making the result not be a sound result. So one way we can overcome that is this. We can pick an individual, for example. I can pick a male who is 36 years old, and I can say, okay, male, age is 36, and I look at their weight. So what is the weight of this person? I'm going to call it weight. I'll call it weight before. So maybe their weight is 159 pounds. And then I can compare it to the weight of the same person after 6 months of going to the gym. So I'll take this person's not going to the gym, and I'm going to say to them, look, I want you to go to the gym, but I don't want you to change anything else in your lifestyle. And I'll measure this person's weight afterwards. And maybe their weight is going to be 150 pounds. So if there is a difference between the weights, it would be likely due to going to the gym, because it's the same person, same age, same gender, same lifestyle. So if this person smoked, we want them to continue to smoke. If they didn't smoke, we want to continue not to smoke. So we don't want them to change anything else between here and here other than going to the gym. And so if there is a difference, we're restricting it pretty much to them going to the gym. And so with ANOVA randomized block design, we can actually extend that result to comparing the means of more than two populations. For example, we may have 3 different drugs, drug A and drug B and drug C. And these drugs all lower your cholesterol. Well, that's what they're supposed to do. And I want to see if the average decrease in cholesterol for the first drug and the average increase of cholesterol for the second drug and that of the third drug are the same, or if they're different. If they're different, some drugs, at least one drug, is better or worse than the other ones. And when I check that, as the previous example, I want to make sure that my comparisons are only comparing the differences between the different drugs. I don't want to be comparing age differences, lifestyle differences, and so on. So if I was to just take a random sample of people from here, and another one from here, and another one from here, some of the samples may be more heavily influenced by males rather than females in another one, or with older people rather than younger people. So to ensure that I don't have these types of issues where the results are going to be influenced by things other than the drug, I can take the guy up here who's a male, 36 years old. Male, 36 years old. And I can give them drug A and see how much it lowers their cholesterol down, whatever it comes down, how many points it lowers it by, I don't know, 20 points. and then I can give them drug B, see how much it lowers their cholesterol down, lowers it by 25 points. And I can give them drug C and see how much it's lowered their cholesterol down. Maybe it's lowered it by 15 points. Now, any results I get from here is going to be based on the same male who's 36 years old. And again, I'm going to tell them, whilst they're doing these drug trials, don't change anything else in their lifestyle. So if there are any differences, it's not because I'm comparing a male to a female or a 36-year-old to a 60-year-old. It's the same person and with the same lifestyle. Everything's kept the same. So if there is a difference or if everything's the same, we know that it's due just purely to the drug. Now, the reality of this is it may be difficult to do this and to block one person off like this, but there's another way that we can do it, a compromise way. And the compromise way is to find a male that's 36 years old and has a certain lifestyle, and then I find another male who's 36 years old who has a very similar lifestyle to the first person, and then I find a third male who again is 36 years old who has a similar lifestyle to the other two, and then I can give drug A to the first guy. So I can say to the first person, male 36-year-old, I can give the second drug to the second male 36-year-old, and the third drug C, to the third male 36-year-old. And these guys are very similar. They're male, they're 36 years old, they have very similar lifestyles, maybe the same ethnicity, maybe the same height, and they all go to the gym, for example, they all smoke, they all have the same lifestyle. So if there's any differences, again, we can get similar results to what we've got above. Any differences will not be based on comparing people that are very different. I'm not, for example, comparing a male 36-year-old to a female 75-year-old. The reason we would do this is because it's going to be a lot quicker, because I can actually run the experiment all at the same time. I don't have to, with the first way of doing it, I have to wait until I've tested the first person, the first drug, and after given them time for the drug to clear out of the system, then give them the second drug, wait for the results, let the drug clear out of the system, then give them the third drug. That can take some time, but this way you can do it all in one go. You can do it in a third of the time or less. So this could speed up the process. It may not be as accurate as the first method because there may be some differences between these people. However similar you try to match people or block people together, they may not be exactly the same, but you do go a long way in taking out these other differences, such as, comparing a male who's 36-year-old with a female who's 20-year-old and maybe who's obese. This would lead to problems in your testing because you don't know if any differences in the drugs are due to comparing males to females, someone being obese and not being obese, and so on. So anyway, there's ways that we can block it to speed up the process. This is another way. And in Excel, when we can run it, we're going to get a bunch of results, and this is a table of results. So K, again, is the number of treatments. So in the previous example I gave you, there would be 3 treatments because there's 3 different drugs. B is the number of blocks. So the B here is the number of blocks. And the number of blocks is how many people I have in my experiment. So if I have 10 people blocked together, so this is just one set of people. This is one block. It counts how many blocks you have. And the error term is like the catch-all term, which brings us up to the total. So in the next video, we'll do an example so we can see how this works. But you need to know or have this at your disposal.